Welcome, everybody, to Southern California Water Portfolio. Just got more drought resistance for our water dialogue. We're going to get started in just a couple minutes as we reach critical mass and people are joining. Thank you all. Welcome, everybody. This is the Southern California Water Dialogue, and another minute or so, we're going to get started as the meeting's getting populated. All right, everyone, this is the Water Dialogue. I'm Connor Everts, co-chair with Dee Zink. She's in Sacramento today, so I will be doing both the beginning moderation and the question and answers afterwards. I want to thank first our steering committee, all of whom are listed there and participate in our planning. So if you have any ideas, get back to us for future meetings. Also, especially our technical team, both from the Metropolitan Water District and always Kathy Caldwell, who is our coordinator for the dialogue and pulls all this together. So our ground rules are simple. We've all been here before, but if you have technical difficulties, use the chat feature. To ask the question, use the Q&A, not the chat. If you have a poor connection, you probably know this, but move closer to your router or turn off other services using bandwidth. I hope none of you were watching French Open tennis like I just was. Your attendee audio is muted by default. So we will do an hour of presentations followed by our dialogue or question and answer session. How to answer the question, hit the Q&A, type in a question, and anyone can upvote by clicking thumbs up on an individual questions to move them higher up the queue.
I found.
So again, this is our process. I'll be doing the concluding remarks, not Dee Zink today. She's with us in spirit. Let's go back to our speakers today. We have two excellent speakers, Dave Pedersen, the General Manager of the Las Virgenes Municipal Water District, and Daniel McCurry, PhD, Associate Professor, Department of Civil and Environmental Engineering from USC. And with that, I ask the speakers to take it away. Thank you.
Well, thank you, Connor. Good afternoon to you all. Thanks for joining. I'm Dave Pedersen. I'm the General Manager of Las Virgenes Municipal Water District. That's my day job. In my free time, I am involved with Water Reuse California and am currently the president of our state section. So I'm going to kick us off by talking a bit about direct potable reuse, the regulations that were recently adopted, why that is a big deal and significant for us here in California. And I will talk a little bit about the regulations. I'm not planning to go into great detail about the content, but I do want to hit on some of the key elements because I think it's important to understand what we're dealing with. And then I will introduce my colleague, Dr. McCurry. So let me pull up my screen there. You should be able to see that. Connor, can you give me a thumbs up if you can see that? All right. So just a little bit of background about me and why water recycling is something so important to me. It's driven largely because my agency, Las Virgenes, we lack local water supply. We don't have any meaningful groundwater to speak of. And so we are exclusively dependent on imported water for our drinking water supply. Because of that, our key water management strategy that we have invested in and have leaned on for decades is water recycling. And we've been doing it since the early 70s and are working right now on really taking our recycling to the next level. So that's a little bit about me and my agency and why water recycling is so important to us. I want to talk a little bit about, just to frame the discussion, the 4 different types of potable reuse. But even before I do that, I just want to acknowledge that potable reuse is one element of water recycling. So there is, sort of a broad series of strategies for water recycling. Potable reuse is only one of them. There's non-potable reuse. There's on-site reuse. So I just wanted to point that out from the get-go. But when you look at potable reuse, the area is divided into 4 different varieties. And they're shown here on this slide: groundwater augmentation, the second being reservoir water augmentation, the third raw water augmentation, and then the 4th treated drinking water augmentation. And what you're seeing here are the symbols that represent the different elements of the treatment strategy, beginning with the urban water use at a home, the wastewater treatment. So you'll see that that is common for all of them, followed by advanced water treatment. And then you'll see the variety in the last 2 steps, the use of a groundwater basin in the top strategy, a raw water reservoir in the second one, and then in the final 2, a more direct strategy involving either water treatment or direct delivery into the distribution system. Typically, the first 2 have been referred to as indirect potable reuse, or IPR, and the last 2 as direct potable reuse. So just a little bit of nomenclature. It's been, and so I wanted to talk about sort of the path to get to where we are. And what I'm really referring to is the fact that last year in December, as I think many of you know, our state water board adopted regulations for direct potable reuse. And it was quite a long journey to get there, dating back 13 and maybe even more than 13 years. Water reuse and our association here in California was a key part of that, along with our legislators. And probably many of you who are listening played a role in this. I'm going to highlight just a few of the critical elements. And what I wanted to emphasize is the role of both research and also legislation in order to drive this. And so if you go back to 2010, there was a landmark legislative measure, SB 918. It was authored by Senator Fran Pavley, who represents my service area, or did represent. my service area and still is a customer here at Las Virgenes. That bill called for two things that were really important. Number one is to develop and adopt what were called uniform water recycling criteria for indirect potable reuse. That's a fancy way of saying develop regulations for indirect potable reuse. And it included a second part, which was to also evaluate the feasibility of direct potable reuse. And that legislation really set the groundwork for what was to follow over 13 plus years. I mentioned research, and part of the key foundational work was to research areas that were not completely understood or that needed more information in order for our regulators in California to feel confident and comfortable that those regulations could be developed. And I should mention what's the goal of these regulations and why are they important? Interestingly, in water, frequently regulations make our job more difficult sometimes, and there's times where we actually are not eager to have new regulations adopted. This was entirely different. This was a situation where the regulations were really providing the structure to advance water recycling. And so it was a very unique and special collaboration where we were supporting the development of regulations really for two goals. One is to ensure that we are protective of public health, and that's a goal that all of us and everyone shares. And the second is to have criteria that would serve as a catalyst for water recycling projects across the state. And we all knew that having those regulations would help to move those projects forward, whereas doing it one project at a time would be less efficient and would lead to a lot of difficulties in permitting. So that was the goal. Research was an important part of that. Water reuse developed and initiated a DPR research initiative. There was a large fundraising effort that brought together about $6 million to fund the research, and that went on between 2012 and 2016. That research helped to support an independent expert panel in confirming that direct potable reuse was indeed feasible. So recall that back in the beginning, it was not even 100% certain that it was feasible to develop these regulations and be protective of public health. So 2016, there was an expert panel report, which was really important, that really paved the way to recognize we could do this and it could be done. The other thing is, in 2017, there was a second legislative bill, AB 574. That bill was authored by Assemblymember Bill Quirk. That took the next step, which was to call for the State Water Board to develop and adopt the direct potable reuse regulations by December 31st of 2023, which was a goal that the State Water Board ultimately did meet, adopting those regs on December 19th, which is the far right here. A few other milestones here: groundwater recharge regulations adopted in 2014. That was the first pathway I showed on my previous slide. And then the final surface water augmentation regs developed in 2018. And then the DPR regs covered both of the varieties of direct potable reuse, those being raw water augmentation and treated drinking water augmentation. So big picture, looking at the role of water recycling in our state, what these regulations really do is help to advance the emphasis that California has on water recycling. There's a variety of reasons for this, but probably most important is that water is too valuable to use only once, and that we have a great resource in our treated wastewater to recycle and recycle more, create a new drought resilient water supply, and to do it cost effectively. Our governor has a water supply portfolio and a water supply strategy And the governor has outlined some really ambitious goals in terms of water recycling for the state. This chart shows those goals and compares them to where we are currently. So the purple portion of this bar is roughly where we are currently, 730 plus or minus acre feet per year recycled. And that was a 2021 number. And I'll just say that number varies year to year, depending on conditions, including whether it's dry or wet and water demands. The 2030 goal is actually pretty close, 800,000 acre feet, and a very achievable goal. The goal to note is the 2040 goal, 1.8 million acre feet. And, you know, I think you can see here, it's quite a lofty goal and will require all of the tools to accomplish. And when I say all of the tools, that includes direct potable reuse. So direct potable reuse is very important in achieving our statewide goals by 2040. So I mentioned that the DPR regs, they're based on reports prepared by an independent expert panel, that the regs for direct potable reuse are much more stringent than for indirect potable reuse, and that is to be expected. Science really drove the process behind this to protect public health, and the report covers that you see here are 3 of many reports that help to inform the process. So the far left, investigating the feasibility for direct potable reuse, that was a report to the legislature. In the center is the State Water Resource Control Board. One of their original framework documents that was put out for public comment. And then on the right is the final expert panel report on developing the regulations. So I mentioned I want to give an overview of the regs, but I don't want to go into too much detail because we could spend an hour talking about that. But I just want to highlight that there are 5 main elements to the regulations, and they're shown here. The organization that is doing the project, or organizations, plural, the chemical control, pathogen control, the monitoring mechanisms and control of the treatment, and then the capabilities, which are referred to as technical, managerial, and financial of the agency that is doing the work. So in terms of the organization that's responsible, the term that you may have heard is DPRA, which is just the acronym for Direct Potable Reuse Responsible Agency. I know that's a mouthful, and so that's why we've been using the word DPRA. In short, the DPRA is the agency that is essentially accountable to ensure that the regulations are met. And you can see on the left is the indirect potable reuse companions. They use slightly different terminology: groundwater replenishment reuse project sponsor, it's also a mouthful, and surface water source augmentation project sponsor. So that is sort of the who, and you'll see that there's a combination of wastewater and water. Essentially, the key element here being the party that is operating and responsible for the advanced water treatment and placing the water ultimately into the drinking water system is the DPRA. So chemical control, a really important part of the regulation, and I would say a distinguishing factor or element from indirect potable reuse. In terms of treatment, train, and process, and this is probably the most technical slide I'll have, is there is a new requirement of an additional treatment process that is unique to direct potable reuse that you will not find with indirect, and that's the inclusion of ozone and BAC. So ozone BAC is required as part of the treatment train for DPR, and it needs to be in the order shown here. So it's at the beginning of the treatment process before RO and UV or advanced oxidation. And the reason for that is chemical control. Source control on DPR is a really important element. Those of you in the wastewater business are familiar with source control. On the drinking water side, maybe a little bit less so, but now that the two are coming together, that it is really important to have a robust source control program to ensure that some of the exotic contaminants are not getting into our wastewater system that is ultimately reaching advanced treatment and possibly passing through that treatment or creating a higher risk in terms of contamination of the drinking water. Pathogen control, this is probably the area that folks focus on the most, although it's just one component, but it is a very important component of the whole because obviously pathogens can cause an acute health risk. We look at it in terms of Giardia virus and Cryptosporidium. And in terms of the treatment requirements, what you'll see here is the log removal requirements. And my colleague Dan will talk more about what those numbers mean. But I did want to just point out that these are quite high. These numbers are large and reflect a very, very high level of treatment certainty and control. So on viruses, what you have is, if you look at those top numbers, the 20, the 14, and the 15, what those are, those reflect 90% of the time, the treatment process needs to achieve those levels of log removal. So 20 log removal for virus, 14 for Giardia, and 15 for Cryptosporidium. So just for reference, 4 log is 99.99. And so if you, for 20 log, you can kind of run that out and count out how many nines there are. You'll see a separate set of numbers there, 16, 10, and 11. And what that reflects is what needs to be achieved before discontinuing the operation of the plant. So there is acknowledgement that there may be times where a certain element of the treatment train may not be completely effective. And because it's a multi-barrier treatment system and there's redundancy, that the treatment process does not necessarily need to stop immediately. And so it can continue. But if you do drop below any of those numbers, 16, 10, and 11, you do need to shut down your treatment system, the delivery of the water to the system, and make notification. So here's a photo. What you see here is Devin Upadhyay, who is the executive officer of the Metropolitan Water District. He's speaking right now at, not right now, but in this photo, which was taken last year in September, speaking at a public hearing before the State Water Resources Control Board and talking about the importance of the regulations for direct potable reuse, and specifically the importance of flexibility to recognize the different types of projects in California that will be coming forward, including a project by his agency that we'll mention a bit later. I'm in the photo on the right. Rick Callender is the CEO of Valley Water. Dave Pettijohn, who is the water resource manager for LADWP. And then on the far left, Shane Trussell, who is the president of Trussell Technologies. So I'm going to stop sharing and just highlight one final point, and then I'll introduce Daniel, is, really going forward with direct potable reuse. What we're talking about is taking water recycling to the next level in California. And there are a couple sort of guiding principles that I think are really important when we do that. And they all revolve around 3 things. I think trust, transparency, and safety. So we have a regulatory framework that's based on science and based on research that shows that we can do this safely. But it's our job as water managers, when we bring these projects forward, that we've got to instill a degree of trust with our customers, transparency, and safety, so that they feel the same level of confidence that we all have, that we can do this and we can do it safely. So with that, I want to introduce Dr. Daniel McCurry. Daniel is associate professor in civil and environmental engineering at USC. He's done research that focuses on protecting public health, very relevant to what we're talking about here, and improving the long-term safety of engineered water systems. Daniel, take it away.
Okay, thanks for that. Hopefully you're seeing the full screen view, not the presenter view. Is that right?
Yes.
Okay, perfect. Glad we got that sorted out. So yeah, thanks, Dave, for the introduction. Like I said, my name is Dan McCurry. I'm an associate professor at USC, and I do a lot of research on water reuse and water treatment. And today I'm going to talk about some of the treatment technologies, maybe in a tiny bit more detail that we use for water reuse. So in other words, what sort of engineered processes does it take to go from treated wastewater effluent, say the water coming out of Hyperion that would be normally discharged into the ocean, which has been biologically treated for, safe ecological discharge, and upgrading that water quality to a point where we can potentially use it as a drinking water source. So before I talk about treatment technology itself, I just wanted to talk a little bit more about what exactly we're trying to get rid of. And Dave sort of teed this up nicely already by talking a bit about log removal and these pathogens. So to start, before I talk about direct potable reuse, for the existing indirect potable reuse regulations, like you said, we have these 3 rules for removal of 3 different types of pathogens: Giardia, Cryptosporidium, and viruses. Giardia and Cryptosporidium are both single-celled organisms. Giardia is commonly associated with sort of drinking untreated water in the woods if you're backpacking or something like that. Cryptosporidium was associated with a major waterborne illness outbreak in Milwaukee about 30 years ago. So that's been at the top of our mind for pathogen control for a while in the water business in general. And then various viruses can make you sick as well. So these are the existing rules for indirect potable reuse, the 10-10-12 rules. And so because this concept of a log removal is often not explained in detail, I thought I would introduce that because I had to honestly look it up for myself when I was a graduate student to figure out where these numbers come from. So to begin, I thought it would be maybe wise to start by talking about just removal or percent removal, which is, I think, the more intuitive way to understand how well disinfection has worked. This corresponds to the number you might see on like, hand soap or hand sanitizer or something like that. So if we do kind of a thought experiment here, removal as a percentage is just 1 minus the number of organisms that are alive after disinfection divided by how many you started with. So to do like a simple example problem here, if you had, let's say, 100 viruses at the beginning of the disinfection step, and at the end there's 1 left, then that's 99% removal, right? That should be hopefully pretty intuitive. Now, the problem with this is that once you start adding more 9s, this gets kind of cumbersome. Like Dave was saying, if you start to run it out past about 99.99%, it starts to get just, a bit unwieldy. And so in our business, we've invented this new way of expressing disinfection effectiveness or the degree of disinfection called log removal. And so how this works, and I promise this is the only slide with math on it in this presentation. For log removal, you take that same n over n naught value, which again is the number of surviving organisms left after disinfection divided by the number that you started with. And instead of subtracting that from 1, what we're going to do is take the minus log base 10 of that number. And in case you haven't done logarithms in a while, I'll again work through a quick example here using the same numbers as I did for percent removal. So for instance, if we have 99% removal, like in the previous example, so if we started with 100 organisms alive and there was 1 left at the end of the process, n over n naught is 0.01, which is 1 divided by 100. And so you can convert that 1 over 100 to 10 to the minus 2. And if you remember pre-calculus class, a log base 10 and a base 10 exponential cancel out. And so you have, minus minus 2, which gives you a log removal value of 2. So that's how log removal values work. And so then 99% removal would correspond to 2 log removal, 99% to 3 log removal, and so on. And so this system is just kind of a convenient shorthand for us once we start to get into high log removal values, because for instance, 20 log removal, which we'll see in a second for direct potable reuse regulations, would be 99 points and then 18 nines after that. So again, just a bit cumbersome. And like Dave said, as we're moving from indirect potable reuse to direct potable reuse, these numbers all get increased for each of these 3 pathogens. So it's the same pathogens as in the indirect potable reuse rules, but now the degree of removal has increased. So for instance, we go from 10 log removal of Giardia to 14 log. And so if you sort of undo that log transformation, that's a 10,000-fold increase in the degree of disinfection, or let's say you can only have 10,000 times, 1/10,000th as many left alive at the end as would be permissible for indirect potable reuse. So these regulations are quite protective of public health, especially for pathogens, which is our number one concern, because it always is in water treatment, whether it's potable reuse or ordinary surface water treatment. And so after we satisfied ourselves that pathogens have been adequately controlled, the next thing that we need to take care of in direct potable reuse are chemicals. And so here, this differs quite a bit from ordinary surface water treatment, because, for instance, if you're treating water from, let's say, one of the aqueducts that brings water to us from Northern California, and a lot of that water is basically melted snow from the Sierras that's quite clean. In contrast to that, wastewater is full of all kinds of chemicals, any kind of chemical that goes down the drain, whether that be, something that's excreted by humans, or maybe something that an industrial, factory or something like that might have perhaps illicitly dumped down the drain. These chemical concentrations are much, much higher than we would worry about in an ordinary water source. So we need to be pretty serious about chemical control. And so, again, first I'll talk about the indirect potable reuse rules and then move on to direct potable reuse. So in California, for indirect potable reuse, you basically have two options for demonstrating adequate chemical control. One requires demonstrating removal of a bunch of different chemicals. I think it's 7 or 8 different compounds. You have to choose one from each of a bunch of different categories, or the simpler way to do it is to demonstrate 0.5 log removal of 1,4-dioxane. So the log removal here works the same as for pathogens, and if you do the math, 0.5 log removal is around 70% removal. The chemical that's been chosen as kind of the indicator of whether chemical removal in general is working well is 1,4-dioxane, the compound whose structure is shown on the bottom right there. And the reason for this is dioxane is commonly found in wastewater. Just about any wastewater you test will have 1,4-dioxane in it. It's a common solvent stabilizer among other applications, so we just use a lot of it as a society. And one of the other key reasons for choosing this one is that it's almost unique in how well it can get through reverse osmosis, which is one of the key treatment steps for water reuse. So if we're doing a good job of 1,4-dioxane removal, we're probably removing everything else pretty well as well. And then as we think about moving to direct potable reuse, a new compound was added. And so you have to demonstrate 1 log or 90% removal of formaldehyde, that compound again shown on the bottom right there. It's a low molecular weight compound. Again, it can get through reverse osmosis very well, which is part of why it was selected. I think another part of why it was selected is that formaldehyde is often formed when you add ozone to wastewater. And as we'll see in a second, ozone is a required treatment step for direct potable reuse in California. So we're kind of getting ahead of one potential complication of using ozone, which again is required by the new rules. And of course, for all these regulated compounds, the reason we care about them in the first place is they're known or thought to be toxic to humans. So now let's move into how you actually get rid of some of these chemicals and pathogens. And again, I'll begin with the sort of existing state of things prior to the new rules that were passed in December. So for indirect potable reuse, where recycled water is sent either to the ground or for surface water augmentation, the kind of classical treatment train that's, I think spread pretty widely across the US and even the world, and this is a pretty close approximation of what's at Orange County Water District, the largest water reuse plant in the world. We have essentially 4 main water treatment steps. There's a few little adjustments here and there, maybe before or after these things, but this is really the core of the water reuse treatment train for IPR. And I'll go through each of these steps in a bit more detail. I have about 1 slide on each of them, but just to name them first, because there might be some acronyms coming up. We first disinfect, often with chlorine, and then remove particles with microfiltration, and then remove even smaller particles and some chemicals with reverse osmosis. And finally, we try to treat any remaining chemicals with UV advanced oxidation. So the first step here is disinfection, and it's a chemical disinfection step that serves really 2 purposes. One is to make sure that we're killing off pathogens. Many steps in the water reuse process are important for pathogen control, but the first one is just simple chemical disinfection like we already do for surface water treatment, or you might do to, sterilize, I don't know, a cutting board or something like that in your kitchen. And so the chemicals that we use for disinfection most commonly are either chlorine, which is literally the exact same stuff that's in the bleach bottle under your kitchen cabinet, or ozone. And I'll talk more about ozone in a little bit once we get to the DPR section. But one other thing I forgot to say is, besides pathogen control, the other important part of the disinfection step at the beginning of the process is that it helps control biofouling. Because the next two steps all involve membranes, and membranes can easily be clogged, including by microorganisms, which can grow in these sort of cakes that we call biofilms. And so we would like to minimize that to the degree possible, so we don't have to spend as much time and effort cleaning membranes, which requires taking them offline. So then the next step in the treatment process is a couple of, or next two steps, both involve membrane separation, or sometimes called filtration, although people argue whether or not reverse osmosis should be considered a form of filtration. But regardless, it's often microfiltration, maybe sometimes ultrafiltration, but those are closely related, and then reverse osmosis. And so I'll say just a few words about each of these individually. So microfiltration, as the name implies, is a filtration step that's meant to remove particles on approximately the 1 micrometer or 1 micron scale. That can be anything from just dirt, I mean, like literally silt particles that might end up in the drain, and also some bacteria or other types of single-celled microorganisms. It won't do anything about viruses, for instance, because those are too small and will pass through the microfiltration pores. But many bacteria can be removed, as well as particulate matter. And part of why we want to remove particles at this stage is that if we leave particles, which again can just be dirt, in the water, it can interfere with some of the subsequent steps. It could lead to clogging of the reverse osmosis membrane, or sort of light screening in the UV advanced oxidation process, which is not really ideal. And then after microfiltration, we have reverse osmosis. And so this is another type of membrane separation process. Again, people argue about whether it should be considered a form of filtration or not. But essentially, the goal of this is to remove almost everything except for water molecules. Sometimes people, as a shorthand, will say that reverse osmosis removes everything but water. That's not quite true, as we'll see in a second, but it does a very good job of removing almost all chemicals. So essentially anything that's charged, any ions, are extremely well removed. That includes just salt, as well as any chemical that's above a certain size. We often, you might encounter a molecular weight cutoff of something like 100 Daltons for things that tend to be removed well by reverse osmosis. So it's a very robust treatment step. It's arguably the most important sort of central water treatment step for water reuse. And like I said, it removes almost everything except for water molecules, not quite everything. So there's been one or two famous episodes that highlighted maybe a vulnerability of reverse osmosis, which is that while it does a very good job for most chemicals, there's a certain formula for a chemical to get through reverse osmosis, and that it has to be neutral, so uncharged, low molecular weight, and polar. It has to have sort of an uneven electron distribution. And so a handful of chemicals that you might expect to find in the sewer can satisfy those criteria. One of them, for instance, is acetone, which is a really common solvent in industry. It's also nail polish remover. And so there was this famous episode at one of the large water reuse plants in Southern California about 10 years ago, where they detected a big spike in organic carbon, which we use as sort of a catch-all bulk parameter for just chemicals, essentially, that might be coming out of reverse osmosis. There was this big spike in both the feed and the product water across the RO membrane at one of these plants about 10 years ago, which was ultimately traced back to acetone, thought to be from an illicit industrial contribution to the sewer. So the point of that is just to say we probably need another barrier after reverse osmosis because it doesn't quite remove completely everything. On the right, there is a pie chart of the composition of compounds that are found in reverse osmosis permeate, the water coming out of the reverse osmosis membrane in water reuse operations. Of course, many smart people have been trying to figure out what exactly gets through the RO membrane so that we can figure out whether we need to do further treatment, and if so, what kind of treatment would work. Much of this sort of pie chart is unknown to date, but we've attributed a decent amount of it to things like solvents such as acetone and certain oxidation byproducts. So that's all to say reverse osmosis does a very, very good job, but it doesn't quite get rid of absolutely everything. And so for that reason, in indirect potable reuse, we also have this additional step of a UV advanced oxidation process. And so I'll quickly describe how this works and then talk about what it's good for. So UV is short for ultraviolet. So an ultraviolet light, it emits really strong photons, the UV light you might be more familiar with is sunlight, kind of the same concept. It's a more powerful form of light than visible light. It's what causes sunburns. It can also disinfect pathogens and break down certain chemicals. But because not all chemicals react with UV light, the particular, let's say, flavor of UV light emitted by these lamps happens to be 254 nanometers wavelength. We help the process out a little bit by adding hydrogen peroxide, same chemical you might have a bottle of in your medicine cabinet. And the UV light splits the hydrogen peroxide molecule so that H2O2 is hydrogen peroxide. UV cleanly splits that molecule in half and makes two molecules that we call hydroxyl radicals. That's that OH with a dot next to it. And I won't sort of bore you with the details of the chemistry, but the main point is that hydroxyl radical is a highly, highly reactive oxidant, meaning it's desperate to steal an electron from the first thing it runs into, which makes it a very non-selective treatment technology. In other words, it will attack just about any chemical you can come up with. It's not picky about what it reacts with, unlike certain other oxidants that we use. And so some of the compounds we care about that might get through reverse osmosis, like NDMA, which is a disinfection byproduct, that's the first compound shown there, and then acetone and dioxane, which I talked about already. The UV AOP step does a pretty good job of tearing apart all these chemicals. And so then getting close to the end here, as we move from indirect potable reuse to direct potable reuse, as Dave said, the new rules require the addition of two new treatment steps, ozone and biological activated carbon. And I'll talk about each of these with one slide or so now. So ozone, as I mentioned at the beginning, is a disinfectant. It's sometimes used at the beginning of even indirect potable reuse plants. And it's a really, really powerful disinfectant. It's very fast at killing pathogens, viruses, and bacteria, much, much faster than bleach even. And another advantage of ozone is that you can make it on site. So all you need is oxygen, and that can be in the form of either compressed oxygen, liquid oxygen, or even just air, which is 20% oxygen, and electricity. So essentially you pass oxygen over what's essentially a giant bug zapper, and it electrolyzes the O2 molecules, the oxygen, into O3, which is ozone. So it's kind of a convenient thing. You just need oxygen and electricity. On the left there is a picture I took last week from a wastewater treatment plant in Switzerland, where they ozonate their wastewater before sending it to the Rhine River. And the center image there is what it actually looks like when you apply it to water. So ozone is a gas, and so you bubble it into water with essentially these giant diffuser things that look kind of like if you have like a little aeration disc in a fish aquarium at home. So same concept. And so the purpose of using ozone in these DPR rules is, obviously it will kill some pathogens, but also it helps with chemical control, because certain chemicals are kind of too large to be readily eaten by microorganisms that we use during normal wastewater treatment. So, at a plant like Hyperion, for instance, we apply microorganisms to break down chemicals before releasing wastewater into the environment, but not all chemicals are easily biodegradable. So the theory here is that ozone can take some of those larger chemicals that are kind of too big of a mouthful for a bacterium, chop them into smaller pieces, and then hopefully they can get eaten during the next step I'll talk about, which is the biological activated carbon step. So there's kind of two ingredients here. The first one is activated carbon, which is, you can almost think of as a form of charcoal. The process for producing it is a bit more complicated than just digging charcoal out of the ground, but it's made of the same stuff. It's essentially carbon with a really high surface area. It's the same stuff that's in a Brita filter if you have one of those at home. And so we use activated carbon for many applications in water treatment, usually as a sorbent, something that's meant to sort of grab compounds out of water. That's the purpose of it in a Brita filter. But for BAC, it's a little bit different. We actually kind of deliberately let this carbon get old and allow bacteria to grow on the surface of it. And so the idea is that because the surface area of activated carbon is really high, we can have a high, like basically large amount of bacteria growing in a fixed volume. And so as we pass that ozonated wastewater with, the larger chemicals having been chopped up by ozone into the BAC column, the thought is that those bacteria can sort of munch on those bite-sized pieces to get rid of some of the chemicals in the wastewater. And so the last thing I'll say, I don't really have a conclusion slide, It's just to mention that these direct potable reuse rules in California that were, again, passed in December, are a little bit unique in that they're quite a bit, let's say, stricter or more protective than the rules for direct potable reuse in certain other states. I won't get myself in trouble by naming any other states or editorialize about whether their approach is better or worse than ours. But some places besides California allow direct potable reuse, or at least are considering allowing direct potable reuse without a reverse osmosis step. So it's just ozone, biologically activated carbon, and then UV advanced oxidation. That has certain operational advantages because reverse osmosis generates a salty brine that you have to put somewhere. Here in California, we can send that to the ocean. In an inland state, you can't. But you do lose the treatment benefit of that additional separation step. So I'm at exactly 20 minutes as far as I can tell, so I'm going to stop there.
All right. Well, thank you, Dan. I think we're coming back to me, and I want to just talk before we go to Q&A a little bit about some of the practical implications of having these regulations in place. And I'll share with you, as an organization, Water Reuse, we have been talking a lot about the fact that we're at an inflection point of sorts in kind of our journey in water recycling. And what we're referring to is that for a decade or more, we've really been focusing on getting the tools in place to allow us to build these projects that will involve indirect potable reuse and direct potable reuse. We now have them. So the question is, what do we need to make these projects happen? And I'll share that there's more work to be done to really answer that question. And I think some of the things like the research, there's more to be done. And so it's not over. And I'll just give you an example. In the area of research, one of the areas that more work can be done is real-time water quality monitoring, like in the area of pathogens. And so there's more work to be done on research, but I do think a pivot of sorts is in order on actually building these projects. And these are large projects, most of them the most expensive projects and ambitious projects that the organizations sponsoring them have ever undertaken. I'm going to try to share my screen. Let me share my screen here for a moment. And I just want to show, if you can see that, give me a thumbs up, Dan, if you can. What that is a map showing the potable reuse projects throughout California. And I'm not going to go through them all, but I just wanted to highlight that there are projects across the entire state. So this is not a coastal issue, an inland issue, or a Southern California issue. This is all of California. There are projects large and small across the entire state that are in different stages of readiness in terms of moving forward, and they're color-coded depending on the type of project they are, whether they're reservoir augmentation, whether they're raw water augmentation, or even in some cases, direct potable reuse. I'm going to take that down just so you can see me, but you can get that graphic from the website, Water Reuse California. Just Google it and it's there. And if you have a project and it's not there, we're eager to add it. And I'll tell you, the second we publish that map, it changes. So I want to highlight a few of the major projects just because they're important. And I'll say yesterday was a really an important day in water recycling, and a landmark day because the Bureau of Reclamation, our U.S. Bureau of Reclamation, announced the grant awards for what they call the Large Water Recycling Funding Program. And two of the three projects are California projects. And so there was a press event that happened at the joint facility of Metropolitan Water District and the LA County Sanitation Districts to receive that grant funding, which was almost $100 million. I think it was $99 million in funding to support that joint project. So that project is called Pure Water Southern California. It's an effort between Metropolitan Water District and the Los Angeles County Sanitation Districts. It involves building ultimately what will be 150 million gallon per day project, and it will be a combination of groundwater augmentation and raw water augmentation, and some combination of the two. There's a demonstration facility that is at the sanitation district's main, what they call their joint plant, that is in Carson. And in fact, that's where the press event was. Another important project and large one is also in Southern California, that's called Operation Next, or you may have heard it referred to as Hyperion 2035. This is also a partnership between two major departments of the city of Los Angeles, the Department of Water and Power, and the Department Bureau of Sanitation, or Sanitation and Environment, as they're called. That project is at Hyperion and intending to reuse and recycle all of the water that is collected at the Hyperion Water Reclamation Plant. The total capacity ultimately, and it will likely be a multi-phase project, would be 170 million gallons per day. So these two projects will likely be the largest in the entire country when they move forward. I did want to highlight the one project in Northern California, recognizing this is not a Southern California exclusive solution, and that is Valley Water. Valley Water has the Silicon Valley Advanced Water Purification Center that was opened in 2014. And they're right now looking at implementing plans to source 10% of their overall demands from recycled water. And they are proposing an indirect potable reuse project for groundwater augmentation and making it what they call DPR ready, or direct potable reuse ready, so that they are able to pivot to direct potable reuse, and that will be 10 million gallons. And then Pure Water San Diego, another important project. Ultimately, that project will source half of the water demands in San Diego from recycled water. It's a multi-phase project as well. First phase, 30 million gallons per day. Second phase, 53 million gallons per day. And that is a reservoir water augmentation. And I'll just mention as well, my agency's project, it's in the backdrop is our demonstration facility. It's a reservoir augmentation project, smaller in scale. It will be 6 million gallons per day. And so it will be among the first, along with Pure Water SoCal, Pure Water San Diego, in terms of reservoir augmentation. So going back to the theme of pivot, I think one of the key areas that is critical is funding. These projects, and Dan described the treatment requirements. These are not insignificant treatment facilities. Robust infrastructure, multi-barrier treatment that is costly, and we're in a time now of really pretty unprecedented inflation. So we are seeing the cost of building major infrastructure go up. And so funding these projects is critically important. A lot of our focus we're going to be looking at is tools to help local agencies and project sponsors to fund the projects, and realizing that funding these 100% with rate revenue is likely to be challenging, and also can push rates up quite a bit in an environment where there is already pressure on water rates. So we are working hard to look at both state and federal funding opportunities to increase and continue the level of investment in water recycling. So I mentioned the federal programs through the Bureau of Reclamation. Those are available through both the Bipartisan Infrastructure Law and the Inflation Reduction Act. At the state level, there is discussion of a climate resources and resiliency bond on the November ballot. And time will tell if that actually comes to fruition, but we've been working really hard to ensure that water recycling is a top line item for that bond, and included to the tune of about $1 billion. So funding is very important. There's also some really great low interest loan programs that are available. The WIFIA program, which is through the US EPA, and our Clean Water State Revolving Fund program through our state. And then the last topic I wanted to hit on, which is a really important one, is communications. I think with DPR, it's going to really elevate the importance of communications. And I mentioned before transparency. So I will just mention the yuck factor. It has not gone away. And although I will say public perception has improved dramatically, there are still folks who are concerned about drinking what was once treated wastewater. And in an environment where we've got emerging contaminants, it does sort of elevate that concern. So our job is going to be increasingly important in communicating how we treat the water and instilling confidence that we can do this and we can do it safely. The notion of toilet to tap has not gone away. I went ahead and said it. And, you know, whether it will ever go away, I don't know. But really, toilet to tap is not an accurate description of what we are doing. What we are doing involves treatment at the highest and most rigorous level of any water in any of our systems. So we are treating this water to a very, very high standard. I do think going forward, communications and demonstration facilities like the one in my backdrop will continue to be important. And there was a time where we did these demonstration facilities to test the technology. And I would say it's shifting. The technology has been tested. We know the technology works. It is more about instilling confidence in our communities that we can do this and that we can do it safely. And so having the tours and having people come in and see the treatment process and understand how it works, and then have the chance to taste the water at the end makes a really, really, really big difference. And also the fact that the operators are critically important. The treatment process is only as good as the operators who are running it. And so having the customers be able to interact and hear from the operators who run the system is really, really important. So I know that we want to leave plenty of time for questions, and I think that's probably a good place to stop. And maybe Dan, did you have any closing thoughts, or should we go to questions?
No, I think that's a great place to leave it. And I think we're pretty much right on time.
So I think, Connor, you're going to help us on questions.
Thank you both very much. There's a lot of good information, a lot of good background. I'm sorry you said the phrase that we've tried to recover from so many years that was used politically, unfortunately, when we were trying to implement the East Valley recycling facility. So as a longtime proponent, as many environmentalists is, of the technology and the solution for local water, I think everyone should understand we've been working on this for many, many, many years. And both the people speaking here and many others are glad that we're finally at the point of implementation. And so there's projects out there. The other one I would put on the list that I've been to a couple soft openings for out of Padre Dam, and a regional group in the East Valley is really good. So they're all seemingly moving forward at the same time. Now there's federal funding, which helps as well. And it's a good investment in long-term water supply, given the extremes, even though we're in the midst of the wettest 2 winters on record. It's predicted we go back to El Nino, from El Nino to La Nina, and a very dry period again. So this is good timing to move forward with climate change. With that, I want to open up to the questions. I've explained before that you use the Q&A feature. I will read the questions, and then we will answer them. We have a hard stop at 1:30, maybe a little bit before if possible. And the chat will remain open for 10 minutes if you want to continue to put information in all of the presentations and the PowerPoints will be available on our website. And I recommend you all follow up and look at other programs we've done. This isn't the first time we've talked about DPR and recycled water either. So with that, we're going to get started. First question from, just so you all know, you don't have to type an answer in. Charming Evelyn says, can the brine be mined for chemical reuse? In other words, is there any other way that the brine byproduct can be used instead of being dumped in the ocean?
I think there's a lot of interest in that at this point, but it's at kind of the academic research stage, or maybe there's small startup companies trying to do that kind of thing. I think, most of what's in the brine, but from a mass perspective, is salt, which is kind of a low value product. And so I think it would be difficult to economically recover that. I've seen some interesting presentations on mining desalination brines where they're quite a bit more concentrated for things like rare earth metals. So that's exciting. But at this stage, as far as I'm aware, it's just research. I haven't heard of any practical full-scale brine mining. Do you know anything about that, Dave?
Yeah, I will say it's a developing area. And actually, now with this question, I kind of think we neglected to talk about brine altogether, which is an important element of this whole equation, or some people will call it non-reclaimable waste. But there is a project in the Antelope Valley. I think it's called Pure Water Antelope Valley by Palmdale Water District. They have a partnership with a company called Capture 6, and they use an electrochemical process to do exactly what I think it's Charming had suggested here. Is it possible to create some usable byproducts like chemicals that could be used for treatment? And so that is their goal. I think there are still a lot of unknowns about that. Would the chemicals be treatment grade chemicals, and would they be of consistent concentration and quality to actually be useful? But there is a lot of technological advancement here. And I think there's promise for the future, but I would agree with Dan. I think they're not quite there. I have not seen one that's quite ready for prime time, but they're close. And so in the future, that is, something that will be a game changer, is if we can make use of the brine in some fashion. Right now, the focus is more around minimizing brine. And there is a lot of proven technology to minimize brine, to essentially squeeze more water out of the brine, which creates more product, which is of value, and then minimize the amount of waste product that we have. So that's kind of been the focal point.
Great, thank you. That was our first question. Now we have 7 more. Evelyn Wendell asks, is there a possibility that DPR can provide extra protection for our drinking water by helping find and implement the solutions to reduce emerging contaminant issues from drinking water?
I don't see why not. I mean, yeah, so obviously the treatment standards are much, much higher for DPR than ordinary surface water or groundwater treatment. And so, yeah, I suppose some of the lessons we've learned about removing, let's say, especially chemical contaminants during water reuse could be applicable for, ordinary water treatment. But I think, actually a lot of the treatment technologies we use for water reuse have been kind of borrowed from other types of water treatment as well. And so, like reverse osmosis membranes, as far as I'm aware, were used for seawater desalination before water reuse. And so, yeah, it's nice to think that sort of technology transfer, if you want, could go in the other direction too.
Yeah, I would agree. I think that there's absolutely chances of that, probably in a variety of ways. One, we're likely to be monitoring the water more rigorously. We will be, for sure. And so we will be seeing things that perhaps we did not see in the water, and that will prompt us in ensuring that it's actually removed. The source control element that I talked about will ensure that some of the contaminants don't get into our water sources in the first place. The prospect of real-time monitoring, I think, offers the potential to detect emerging contaminants. So I think the answer is yes, it will.
Okay, great, thank you. Charmaine Evelyn again says, although I know the answer, I will ask for others, how does this work by removing PFAS and PFOS?
So I'll kick this off, and then I'm interested in Dan's thoughts. So this, PFAS is so much in the news that it is a focal point. And the fortunate thing is that reverse osmosis is very effective in removing PFAS. And we have, we know that, and we actually do testing in our demo facility, and we show it. So PFAS is no doubt, it is in our treated wastewater. It's in all treated wastewaters of different concentrations. So we do see it come into the advanced water purification facility, and we can show that it's not coming out in the treated water. So then the next logical question is, well, where did it go? Right? And it unfortunately is not destroyed in the treatment process. It's rejected in the brine. And so we do find PFAS in the brine. And that is sort of a future issue that needs to be dealt with is PFAS, and how do we deal with that? And I anticipate that will be the subject of perhaps future regulations in removing PFAS so that it is not damaging to the environment. So, you know, a lot of the focus on PFAS has been around human health, and the most recent MCL is focused on human health. But I think we all realize that there are likely environmental impacts to discharging waters with PFAS. And so more work needs to be done on what levels are problematic, and then how do we mitigate that. So I think that's an area of more work, and likely something we'll see in the future that we'll need to be prepared for.
Good points. Thank you. So the next one is anonymous, but it asks, it includes PFAS, but also asks if you could both speak to how well these processes address pharmaceuticals and emergency contaminants of concern. Does the regulatory framework support adaptation for new information?
Maybe I can answer the first part and Dave can take the second. So I was just going to say actually that PFAS is kind of a nice example illustrating how powerful a barrier reverse osmosis is, because you know, the reverse osmosis membrane was invented before anyone cared about PFAS or knew it was in drinking water, right? And then it turns out the reverse osmosis we were already using for water reuse removes like 99+% of the PFAS, because it's such a powerful barrier for removing almost anything. So yeah, I mean, I think the treatment processes in place are very powerful chemical barriers. Reverse osmosis doing the heavy lifting, and then the advanced oxidation kind of doing cleanup afterwards for any, like I said, really, really small chemicals that can occasionally sneak through. So short answer is yes.
Yeah, I would agree. You know, on the pharmaceuticals, something I always ask people to do is when you get your medicine, open that there's that little piece of paper, that little fold out paper that's usually stuck to it, and we usually throw away, is peel that off and open it. It always shows the chemical structure of the medicine or the compound. And what you'll see is these are very large compounds. I mean, the diagram doesn't necessarily reflect exactly the size of the molecule, but it gives you a sense of the complexity. They are large molecules, so they are well and easily removed by RO, which is fortunate. On the second part of the question, the regulatory framework supporting adaptation to new information, I'll share that was one of the critical areas that we really weighed in a lot on and made comment about. And we did encounter a little bit of pushback in that the regulations are pretty prescriptive. And we did really want to see the regulations incorporate flexibility, realizing that treatment technology is a dynamic field, and it's developing and evolving, and it will be improving. And so we wanted to acknowledge that. And I'll say we did succeed to some extent, that there are places in the regulation where it does allow adaptation to new information. But one of the key elements for that, which is probably a good safeguard, is that it really needs to be validated by the independent expert panel. And so that there will not be sort of alternatives where public health would be compromised. And I think that's really important. And that was the goal of the Water Board, is that they wanted to be sure that any new information, as it was incorporated into the regulations, does not compromise the effectiveness of the regulation.
All right, thank you. And then there's another question further down by Rajat that says the new PFAS regulations is the new regulations prompting a revisit of the treatment of DPR? And could you share our understanding on California and outside California treatment trains for DPR?
I think so. We already talked about how well reverse osmosis works for PFAS, which is required in California for water reuse. I think PFAS is sort of triggering a bit of reconsideration of some of the treatment trains used in other states. I mentioned in my very last slide that in some, especially inland states in the West, reverse osmosis free water reuse, or sometimes called carbon-based water reuse, is permitted. And so if you give up reverse osmosis as a treatment step, there's a lot of sort of backfilling to do in terms of treatment capacity for removing things like PFAS. This is still, like I would say, an active matter of research and debate about how we ought to think about RO-free water reuse. But yeah, it's tough if you give up reverse osmosis.
Okay. There are some others that are just comments really rather than questions, but John Molson asked if you could show the chart of the agency or projects in Southern California, and he's asking what percentage of the water usage in LA County could come from potable reuse.
Yeah, I can pull up, should I pull up the chart again? I can do that.
That'd be great, thanks.
You should be seeing it now. I don't know offhand what percentage, and I'll just say that it's rapidly growing. So with the two projects, with the two major projects in the greater LA area being Operation Next and Pure Water SoCal, it will dramatically increase the locally sourced share of water in the LA County area. I don't know the numbers or percentages just off the top of my head, but I know that it will be significant.
And I think maybe one important note for calibrating expectations here is that it will never be 100%, because even if, for let's say, when we recycle 100% of the wastewater, that's still less water than we use. Because if you think about all the water you might use at home, not all of it goes down the drain, right? If you water some plants outside, for instance, or if you wash a car or something. And the other thing is sewers leak. They just all do. That's the fact of life. And so not 100% of the water that goes down the drain makes it all the way to the wastewater treatment plant. Plus, in the water reuse process, at least if we're using membranes, a little bit of the water is lost to brine. So I think absolute maximum might be 50%.
Okay, and you can probably add or subtract as we all do greater efficiency levels too. There's less water flowing through. So Amy asked, can you elaborate on the monitoring and control piece of the pie? What types of local limits will be added that are particular to DPR? Is it only pertaining to the source control, or is it additional monitoring within the treatment plant as well?
I was just going to say all of the above. It's not just source control. There's quite a bit of additional monitoring throughout the system. I'm just looking through my notes here. I don't have specifics on the actual monitoring that's required. It is in the regulation. There's a section entirely on monitoring. And, the monitoring is really, really important because as you go to DPR, direct potable reuse, you have less time to catch and correct and address a failure in one of the treatment trains or a treatment process. So with indirect potable reuse, where you're placing the water in a groundwater basin or a reservoir, if you have an issue or a problem, you have time, a response time, to go and stop that water from being delivered to the customer. So now with direct potable reuse, you have less time, in some cases, very little time. And so you need increased monitoring in order to ensure that quality, those quality goals are being met. I don't know if Dan, you have any of the specifics on it, but.
No, yeah, I mean, I agree with everything you said. I don't have any special secret information on monitoring. It's not really what I work on, but yeah, I agree with what you said.
Okay, thank you. Next question, Thomas Bunn says, how small can treatment facilities be for DPR? Can an agency have multiple facilities in its service area?
I think it's conceivable and possible. I haven't seen that proposed as of yet. It sounds a bit like sort of, can DPR be brought forward in the form of sort of distributed infrastructure is what I'm gathering there. There is a level of economy of scale in building these treatment systems. So I think probably there would be some challenges in building multiple very small facilities. But I also would say it's probably not out of the question. It's probably possible. It just may drive up cost, like unit cost of the treatment, because they're pretty complex facilities. And so you tend to see them in the form of the larger, more centralized systems.
Yeah, I completely agree with that. I think there was a lot of enthusiasm for decentralized water reuse starting maybe 10, 15 years ago. And I think that's not a bad idea for things like gray water reuse for irrigation. But for DPR, the burden for protecting public health is so high that I don't think it's necessarily wise to have 100 different little tiny plants that each are visited by one part-time operator 1 hour per week. I think the onus on us to keep that water extremely safe is high enough that it's probably better to do it in a centralized fashion.
Right. Versus actual industrial reuse where you may have plants on site as well and smaller, decentralized. All right, Dr. Tom Williams is asking, can brines be injected into oil-filled water drives such as under the Long Beach Harbor, the Port of LA, and Santa Monica?
Maybe. I haven't really thought about that. I think in coastal California, because we can do ocean discharge, it seems sort of unlikely that they'd be injected, but maybe if there's tighter regulation on brine discharge in the future, I don't know.
Right.
Yeah, there could be, deep well injection has been talked about. It's done in Florida quite a bit. There was an effort in the Santa Clarita Valley looking at deep well injection, and it didn't move forward. It got a lot of community concern and opposition. So it is a strategy, but it hasn't really gained traction in California from what I've seen. This looks a little bit more like coastal well injection, which might be slightly different, but I think it's an intriguing idea. I just haven't seen it happening yet.
Okay, great. I don't know is a good answer sometimes too. Anonymous again wants to know what the potential cost per acre foot of a typical potable reuse, or at least a range.
I have a number in my head, Dave, but yours is probably more accurate.
I was going to go with the range. I know GWRS, I think, to their credit, I think pretty much sets the low end of the standard in terms of cost, as they're large and really effective and efficient. I think somebody correct me if I'm wrong, but it's in the neighborhood of $600 an acre foot. And then the numbers can go up, quite a bit depending on the size and location. So up to, over $2,500, even maybe $3,000 an acre foot. So I think it really depends on the circumstances, how far you have to go to dispose of your brine and some of the kind of site configuration challenges. But I think there's a pretty wide range.
So that sounds like expensive water, but then it's also has multiple benefits out of it as well, including not discharging directly into the ocean as we did historically. That I believe $850 was the last number I heard from Orange County on the lower end. But you could also compare it to what the Poseidon desal plant is going to cost San Diego County Water Authority next year, which is $4,000 an acre foot. All right. Charming Evelyn again wants to know any thought on inland DPR, what they do with their brine byproduct.
Yeah, brine disposal can be sort of an Achilles heel for potable reuse. So inland areas, there are some inland areas that are fortunate that they have access to a brine pipeline. The Inland Empire and what's called the Sari line. They're fortunate that they have that. There are areas that do not. My service area is one that does not have access to a brine pipeline. So we're building a 14-mile pipeline to connect to a brine pipeline in Ventura County. So it can be a real challenge. I think there's future technology that, you know, we're all hopeful for about zero liquid waste technologies. Again, it is still not, I think for the most part, not ready quite for prime time, and they're pretty costly. But the other thing is, you know, the option of drying beds. You know, you look at a place like the Antelope Valley, where you've got open land and you've got really a hot climate, is, you know, you can put the brine into a drying bed. That's not really an option for my area, but in some inland areas that could be an option.
Okay. And, you know, as you mentioned, there, we may be limiting brine discharges into the ocean as we learn more about those impacts as well. They've certainly looked at that in the Monterey area, Monterey Bay.
Yeah, we didn't really
Grant,
talk about that. That's probably a good environmental benefit of these projects, is driven by reducing not only ocean discharges, but even inland waterway discharges, and helping to improve water quality.
right. You're still going to have a concentrated brine discharge, right?
Right.
You
Yeah.
will, but you know, I guess one, you know, way that this compares favorably to, let's say, desal, is a brine from water reuse is probably still less salty than the ocean. I mean, not
Right.
to say that other chemicals in there might not be of concern, but at least, you know, in terms of creating a salinity hotspot, that's not such a concern.
Good point. All right. Grant Hogue asks, how critical is the sequence of oxidation and GAC as the first two steps rather than later in the treatment process?
I think
Yeah,
depends on who you ask.
so that's a good question. Grant, I think, is thinking ahead to some. So it does create some challenges where it's placed in the treatment process, especially for projects that I would call a combination project. So a combination project is one where it involves an element of groundwater replenishment and recharge, and an element of, say, raw water augmentation. So it's sort of straddling the IPR DPR line. And so the requirements are different. And so you really want to apply the higher level of treatment, namely the ozone and the GAC, only to the DPR portion. But because of the place where it is in the treatment train, you kind of end up having to do it for both. So that is an area where I think some future work is warranted to look at that. How do you do that most effectively? And I think probably some research on that is worthwhile on sequencing it. But the regs do call for that to be at the front of the treatment process right now, and they have some reasons for that. So I think some more work is needed on that.
Yeah, and I'm aware of at least two utilities that are interested in getting an exception to that, you know, specified order. But I'll just quickly say that if you mix up the order, you lose some serious treatment benefits in terms of the water coming out of the ozone BAC process is much cleaner, and so you can go longer between cleaning the RO membranes, and also the brine created by the RO membranes looks a lot better. So yeah, in my opinion, you know, all else being equal, the current sequence specified by the regulations makes a lot of sense to me. That's not to say it's unsafe to do it the other way, just maybe a bit less efficient.
All right, thank you very much. And Doris Solaris says, what is the residuals of the brine and where is it disposed of? That's kind of what we've been talking about already. But did you have anything else you wanted to add to that?
Yeah, just the residuals are, I mean, the makeup of the brine is really, you know, determined by the source water, right? So it's the reject water from the RO. So you really have to look at the source water. And they are all different. You know, my service area is almost exclusively residential. So I like to say we have good wastewater. But, you know, so if you have a lot of industry and manufacturing, you're going to have a little bit different wastewater, which is going to result in a different composition of brine. So it depends. Of course, the commonality is always going to be the salts. And so salt is always, you know, you're going to find that in the brine. And generally disposal right now is generally through a brine pipeline and ocean discharge currently.
Okay, there are some others, but we're kind of running out of time. I do want to say a lot of people said they really appreciated your presentations and your comments, and now the answers to this as well. Someone was asking if we could get copies of the slides. For example, the map showing California projects was too small to read. That is on the water reuse website. Is that correct, Dave?
Yeah, it is correct. And I'll send it to you all as well so that you can post it or cross-post it.
Okay, great. And then people could blow it up on their own.
Yeah, it is a little
Okay.
tough to see, sorry.
Yeah. And no, in general, this was an excellent and timely program. I appreciate it a lot. If people still have questions, they can continue to post them to the chat. I do need to say that, so thank you to the presenters and thank you all of you who are on today. I did want to make sure that we mention that we are coming up with our next presentation in June. And it will be about water quality focused meeting, which will feature 2 state water resource control speakers from the California Water Quality Monitoring Council who will talk about water quality data resources available and the plans to further develop and access these resources. Evelyn Wendell with WETAP will discuss the ongoing work to reduce dependence on single-use plastic bottles, improve drinking water quality, and increase access to public drinking water fountains and the important role utilities play in these efforts. And with that, good night and good luck. Thank you all very much.
Thanks.
Thank you. Bye-bye.
That was excellent.